Welcome back, everyone. So it's time to get started. This is now the afternoon program of the ANRW workshop. I'm Anna Brunström, up here together with Ryan Beckett, and we're sharing the workshop. We have a lot of exciting presentations left. So before the coffee break, we will have a session on transport and then a session on a poster session, started with some lightning talks. And we ask the speakers to keep to the very good practice from the morning to keep your presentations to 10 minutes. And then we have time for also some nice discussions. And please join the queue if you have questions that you would like to ask. And remember to also introduce yourself when you come in the queue.
Okay, so for the first talk is going to be getting up to speed with Nico and careful resume. This is from Nikolai Fischer. This was work as part of his master's thesis from Friedrich Alexander University. And he's interested in transport protocols and networking and is currently looking for a position to continue this or similar work. So if you're interested, talk to Nikolai afterwards.
Thank you for the nice introduction. So I think you all remember a time when you were downloading a file and you were looking at the download speed and noticed it takes a couple of moments to get up to your full bandwidth capacity. And I think we all know why this is, right? This is because of slow start. Normally our congestion controllers, they start out with a small initial window and then gradually increase that window for every acknowledgement they receive. And this is what you can see on the left graph. We have here a transfer with Nico. And you can see that the entire transfer time is during slow start, and it really takes a couple of RTTs really to get up to any meaningful speed. Now, why are we doing this? We don't know our network's capacity initially, so we do need some sort of careful probing in order not to overload the network. But in reality, a lot of times we kind of know our networks. Right, so we're connecting to the same endpoints over and over again. Think about CDNs, think about loading different pages of a specific web page connecting to the same web server over and over again. And with careful resume, we aim to reuse this knowledge from previous connections in order to get up to speed more quickly. And this is what you can see on the right side, where we can increase our sending rate much sooner. So we can complete our total transfer in less than half of the time that slow start would traditionally take. Now, how can we do this safely and securely? So careful resume starts out in the reconnaissance phase. And the purpose of this phase is to check whether this path that we're currently on matches a path that we've been using in the past. And to do this, we're using an RTT estimate. So we're comparing the current RTT during the handshake and the initial data towards the saved parameters. And if it's not in an acceptable range, we don't do anything specific to careful resume, but instead continue to the normal phase, which means we're letting the regular congestion controller do its normal slow start thing, because we don't want to apply parameters from a different path to another path. Now, if the RTT is in range, we continue to the unvalidated phase. And the purpose of this phase is to jump our congestion window to half of the saved parameter. So we're not trying to resume immediately at the full sending rate that we're using previously, but the half. Now, once we've sent this jump, as we call it, we are transitioning to the validating phase. Now, in this phase, we're receiving the acknowledgements for all of the data that we have sent during the unvalidated phase. And if everything is acknowledged without loss, we can continue to the normal phase. During the validating phase, we're allowing the congestion controller to continue to grow its congestion window according to the normal rules. So for Cubic, that means at the beginning of the normal phase, we will have fully restored our congestion window to that saved parameter. Now, what happens if the network conditions have changed? Maybe the path has some other utilization. Then we will see loss events during the unvalidated or validating phase. And to handle this situation, we have a special mechanism in careful resume called safe retreat. Safe retreat does a little bit more than traditional congestion avoidance. We start out by first reducing our congestion window and then blocking its increase until the last packet sent as part of the jump has been acknowledged. And then we're setting the slow start threshold to what we call the pipe size which is the cumulative sum of successful acknowledged data during that time. So we're exiting careful resume with a set slow start parameter, which will then limit the continuing growth of the congestion window, because we've now determined that our optimistic jump has failed. How have we evaluated careful resume? In this paper, we have implemented careful resume into Neko, which is the quick stack used in Mozilla Firefox. And the main challenges for implementing careful resume is, on the one hand, buffer management. Now, this is, I think, a challenge for all quick implementations, right? You have more to manage than with traditional TCP, where you can just submit data to the kernel. And especially because of the jump in the unvalidated phase, you might be tempted to submit a lot of data into your socket buffers at once, and you have to make sure not to overwhelm those. And the second and even more important challenge is pacing. Because we're jumping our congestion window by potentially multiple megabytes at once, we need to make sure that we're pacing out that transmission over one RTT. Otherwise, we can be fairly certain that we will introduce losses. And that's why we need explicit pacing. And depending on your platform that you're targeting, that might require different timer mechanisms, and that's certainly the most challenging thing to implement properly. Now, how does all of that look in practice? Careful resume was initially thought to provide the largest benefit for especially high latency paths, but our experiments show that the benefits apply to high BDP paths, so high bandwidth delay product paths. So to visualize that, we have this experiment that shows paths ranging from 10 megabits all the way up to a gigabit speed, and from 10 milliseconds all the way up to 600 milliseconds. And as you can see, the benefit, so the speed up of careful resume over slow start for an object of BDP size grows with the BDP. So not just high latency paths benefit, but also very fast low latency paths. For example, the gigabit 10 millisecond path you can see in the bottom right. So to validate those findings in the real world, we took a select paths that we had access to and run measurements ranging from transfers for a quarter BDP up to 20 BDP. And as you can see, the absolute time savings, so careful resume can always outperform slow start in these situations. And the absolute time difference is in the range of several RTTs, which can be a significant impact on your end user experience. So for example, if you look at the 5G cellular connection, if you were to upload like a typical image file, for example, 5 megabytes, you would see a time reduction in several RTTs, so a few hundred milliseconds. So if your user in its app is waiting for this upload to complete, that would make a real impact on your end user experience. Now, of course, if you look at the larger transfers, the relative benefit decreases, right, as the steady state performance of the congestion controller is the most determining factor here, and the absolute benefit remains the same, right? Careful resume manages to restore the congestion window to the safe parameter, in the ideal case, in about 3 RTTs, and depending on how large your BDP of the path is, you save a multitude of RTTs, but once slow start is over, your benefit is there. So that means especially small transfers, which we think make up a lot of today's internet traffic, look at web pages, interactive workloads, would benefit greatly, because most of those always remain in slow start. You might never transition into a steady state phase. Now, while these experiments show that careful resume works in an ideal case when the path is not congested, what happens if the path is now utilized by other flows? To evaluate this, we have run the following experiment. We have a number of background flows from 1 to 16 that transfer 100 times BDP of data in total, spread among them. And we're giving those flows a couple of seconds time to equalize and sort of reach a stable performance. And then we're jumping in with another flow, either with slow start, which you can see in orange, or with careful resume, which you can see in blue. And this experiment shows that the losses we're introducing into these background flows, so the harm we're causing to other flows that are already using this congested bottleneck, for careful resume is not much more than for slow start. So in terms of fairness, we're not much worse than traditional slow start, but the benefit for these flows with careful resume is still that their completion time is lower than slow start. So we're still faster, even if the path is already congested. And that's just because we're initially ramping up our congestion window quicker. Then once we're receiving the losses, we're pulling back with safe retreat. But this initial amount of data we've been able to send still offers a speed up compared to slow start. So in conclusion, careful resume is an enhancement to slow start, right? If the path doesn't match, which we're determining in the reconnaissance phase, we're falling back to traditional slow start. But if the path does match, we can see significant performance benefits. And we can see those performance benefits over a wide variety of internet paths, and especially high BDP paths benefit. And as the heat map tried to show you, most modern internet connections that you might have on your phone or at home are what we would consider high BDP paths. And a large portion of internet traffic is also, or at least interactive traffic, is small file transfers that would benefit greatly. And finally, we've shown that careful resume does not result in any undue congestion or harm to other background flows. Now, what's next for careful resume? We would like to see more wide-scale deployment, and I think our implementation with Firefox might be one of the first ones that could be deployed on the client side. But we're looking for more performance metrics from, like, for example, CDNs or big deployments. Thank you.
Any questions?
Lars Eggert, Mozilla, while I'm trying to get into the queue. Thanks for doing work with our stack. So I had a question on the thing you said at the end. So you looked at the number of loss events during over a congested path. And you said that there's more, but it's not much more aggressive, and it also completes faster. Have you looked into the impact on the competing traffic at all? Because if you could say, well, look, the competing traffic isn't much slower either, I think that would make it a very strong point. I'm willing to believe you, but I would like to see the measurement.
Yeah, so we've looked at that on the data set itself. So the flow completion time for the background flow doesn't change dramatically. So we haven't included it in the graphs right here, but that's what I meant. Like, we would like to do more measurements and look at this in more detail. But what we've seen in general is that careful resume doesn't, or is not able to acquire an unfair share of bandwidth. So in the end, like, once it has settled in, it will occupy a fair share of that congested bandwidth, just as slow start would end up. So the flow completion time for background flows does not change dramatically, at least in the tests that we've run so far.
Yeah, that's a great answer. Thank you.
Raffaello, University of Berlin. Yes, I see that careful resume is a little bit aggressive when you compare it to the slow start, for example, no? But it would be interesting for me also to look at the case where you start with a larger initial window, because there have been a lot of debate at the IETF if 10 is the right number. We thought maybe to scale to higher number, like 64, 100 even was floating. So it would be interesting to see, for example, maybe you've done that, what happens if the congestion window start larger as the BDP. In that case, what would happen to the loss rate?
So we haven't specifically run that kind of experiment. I know there's definitely interest from, I think, Fastly to try to use careful resume with a fixed size jump to, like, instead of using initial window of 30 or 60, using careful resume to do a fixed size jump of, for example, 60 packets. But personally, in this stack, we haven't run any such measurements. We have only run measurements like as the current sort of draft intends. Yeah.
Yes, we've done also some tests with careful resume, and we have seen that effectively is useful to add those phase like safe retreat that kind of backtrack faster, so to avoid all those losses. So it would be interesting to see it. Thank you.
Okay, thank you, Nikolai. So our next speaker is going to be Johan Garcia from Karlstad University, and he's going to talk about TCP congestion control performance over Starlink.
Okay, great. Thank you for the introduction. So we'll talk about measurements performed using the Linux TCP implementations over Starlink. And to provide some background, as most of you know, Starlink provides internet connectivity with the help of many thousand satellites orbiting the Earth. They have many millions of customers. In particular, we can see that here approximately is where Costa is located. So we are somewhat outside of the main distribution of satellites, but we still, due to the way that the vision from the antenna is, we have very good coverage still. Okay, so there are some technical aspects that could be good to keep in mind, in particular the 1.33 millisecond frame time that is used in Starlink. So this affects the microscopic behavior of resource allocation in Starlink, which, as it turns out, has some impact on the macroscopic behavior in terms of TCP throughput, which we will discuss later on. Also, on longer timescales, we of course have the 15-second reconfiguration losses, and there can be some spurious losses as well. Okay, so the things that we will look at is congestion control performance for different variants, how it works for different flow lengths, fairness aspects, and longitudinal aspects. So we have been doing measurements for 2 years now, and we could draw on that to make some longitudinal comparisons, which are rather interesting. Okay, so the setup is that we use our standard dish generation 2 at Costa University with no abstractions. We use iPerf, capture the TCP dump, examines the PCAPs basically. We run the experiments for 180 seconds, so that's very long. These are like for the baseline results. We do it with 1 or 10 parallel TCP flows, and we perform 15 replications in measurement blocks. So we have 15 measurement blocks where we measure the different congestion controls, and we randomize the order within these blocks. Okay, so time for the initial results. So here is the overview of the relative congestion control performance for the different TCP variants. If we look furthest to the left, we see kind of a baseline, what we get if we use UDP and set it to transmit at a rate of 500 megabits per second, and we receive on the median of the average of these 15 runs is somewhat above 250 megabits per second. And we also set up, just to validate, using 10 UDP flows of 50 megabits per second as well. And they match very closely to the single 500 megabits flow. If we now look at the TCP variations, we see that BBR in the single flow case comes fairly close to the expected average available bandwidth, but doesn't really come up to the level of UDP. If we have 10 flows, then more or less we are at the same place. And I can say that as a visual help, if the boxes in this box plot overlap, then you could, in a somewhat simplified way, say that there is no statistically significant difference. It's not like a formal statement, but just as a help when considering the results here. So if we continue now and look at what happens with cubic, and in particular the two variations of cubic, which has either high start enabled or no high start NH. So we see that, okay, in the 10 flow case, they are able to use the capacity fairly well, but in the one flow case, they are having severe problems. This is true basically for all other evaluated congestion controls as well. Illinois is the best performing out of the remainder. The delay-based congestion controls perform really poor. We haven't really looked into the details of this, but as I mentioned, we have these frames, and it turns out that you are not actually allocated in typical case continuous transmission resources. So there will be small pauses that will basically mess with your delay measurements, round trip time measurements, which we will touch on a little bit later on also. Yeah, so we can also say that if we look at the ratio between the throughput for 10 flows versus one flow, we see that for cubic, it's on the order of 5 times larger. So if we would make the assumption that the poor performance is only due to randomly placed losses, you could argue that we could expect perhaps this to be closer to a factor of 10. So that we can perhaps take as an indication that there are other factors here as well. And other people has made similar measurements and came up with to a large extent, similar results. This includes Jeff Houston and other academical papers as well. Okay, so let's go on and have a look at some selected runs. What is particularly interesting here is that we see that in these runs that show the maximum performance for some selected congestion controls, we see that there are some horizontal streaks here. And this is basically an indication of full utilization of the capacity that Starlink can offer. And the particular position of that streak is a function of the burst length, the interburst time, and the modulation that is used on the frames, which we have studied in earlier work. Excuse me. Okay, so if we now move on to looking at what happens if we consider shorter flow lengths. As we know, most of the flows of the internet are not as long as 180 seconds. So if we look at what would the effective flow throughput be for different flow lengths up to 1000 kilobytes, that is shown in the upper graph, and the lower graph shows the completion time based on the same data, of course. And we can see that here there is not a huge difference between the congestion controls. Slow start behavior dominate for these shorter transfers. If we consider somewhat longer transfers, here differences really start to appear. We see that Vegas and regular cubic compete for being the worst. And the problem here, we can see that it is related to high start, because the cubic without high start, which is the gray line, performs quite well over this flow size range. And finally, if we go to really long flows, we see that here, and the performance starts to tend towards the long-term average that we saw in the first graph. Okay. Another thing that we looked at was the fairness of these different congestion control variations. And not really unexpected, BBR version 1 is really unfair, especially against cubic. BBR v3, and this is the variant from March this year, performs much better. So that is quite fair. And the unfairness is there regardless if we start BBR first and then cubic, or cubic first and then BBR. Illinois is able to fight off BBR better than cubic, we can also observe. We can now leverage some of our previous measurements as well and see, okay, this very poor performance of cubic, how has that actually evolved over time? So we see here, the first measurements are from July 23, and they are still 180-second IPERF measurements. At that point in time, single flow cubic gave a throughput above 100 megabits per second. Then in our second measurement run in February 24, we see a very drastic reduction in single flow cubic throughput that holds all this way. So something has happened here. This is also visible in the horizontal aspects for cubic, which we see up here, but not for the other ones. Okay, so to conclude, we find that BBR-V3 is the best performing congestion control from an overall perspective, also considering the fairness. We also know that the microscopic behavior of Starlink in terms of transmission resource allocation and delay behavior has an impact on congestion control. And that is something which is good to keep in mind if you make emulators or simulators and want to evaluate congestion control performance. And with that, I conclude my presentation, and thank you for your attention.
Hi, very interesting results. I wonder, do you also have results comparing upstream uplinks versus downloads?
No, we haven't looked at congestion control for the uplink. We have done now recently delay, one-way delay characterization for uplink and downlink. So perhaps that is something we'll consider in the future.
Thank you for the talk, very interesting. So I was wondering why iStart++ doesn't perform that well. iStart, is it iStart or iStart++? Is it the version that, because
it would be the iStart++. That's we were using Linux kernel 6.8, the default in
yeah. What do you think is need to be fixed in that? Because my understanding is that those timing issues that the first version of iStart were kind of addressed in the iStart++. Do you have any insight on this?
Not really, no. But perhaps you can get some, because iStart partially works on the delay aspects, and we have now just recently done this detailed delay characterization, which shows that if you measure delays with pings, like every 5 milliseconds or 10 milliseconds, something like that, you cannot actually appropriately understand this microscopic behavior and the delay effects on the microscopic behavior, which has higher considerations than for like the behavior of the congestion control. And it potentially could have implications also for iStart++ behavior.
Thank you. Jeff Houston, thank you. It's interesting talk. I was wondering, do you have any intuitions as to the characteristics of the Starlink carriage service that creates such radically different responses from the various transport protocols you're testing?
So I have some speculative ideas, which I prefer not to tell at this point in time. What I plan to do is, well, basically, previously I have done a detailed macroscopic and microscopic examination of throughput variations in Starlink. Now, recently, we have done a detailed study of the microscopic delay variations of Starlink. Upcoming is a detailed characterization of the loss characteristics in Starlink. As I list here, we have at least 4 different sources for losses, so we want to understand that in detail on the microscopic level. And when we do that, then the next step would be perhaps to do some good queuing characterization. What exactly is the queuing? How does the queue behave in Starlink? When we have those 4 components, we have all the necessary parts to understand the complex interaction between this time-varying link behavior and congestion control. So that's the plan.
Thank you.
Lars Eckert, Mozilla. I have a quick question about your first bullet there. BBRv3 is promising for Starlink. Is it only promising while there's still other congestion control traffic around that it can steal capacity from, or is it really good at capturing otherwise idle capacity, and it will be good for Starlink even if all traffic is BBRv3?
So Starlink assigns each user some capacity, and whichever congestion control you have, you can't get more resources from Starlink if that is fully allocated.
Okay.
So what you can compete is like traffic from other servers to you as a user. But we see here that BBRv3 actually is relatively fair. I mean, the worst case is a factor 2, which is much better than the factor 8 that we see for BBR version 1.
Okay, so basically your experiment is sheltered in its own little slice from the other users, and it's just better at using
that's how
underutilized
Starlink
capacity.
does the resource allocation.
Okay, thank you.
Okay, thank you, Johan. So our next speaker is going to be Ahmed Saeed. He's an assistant professor from the School of Computer Science at Georgia Tech. He's interested in theory, design, and implementation of scalable computer networks and computer systems, including resource scheduling, congestion control, operating systems, and formal methods. And he's going to talk about understanding QUIC's throughput speed bumps.
Hi, can you hear me? Sorry. Oh, okay.
Yes.
Okay, so thank you for the introduction. This is work done by my students, Shabiq and Dami, in collaboration with my colleague, Mustafa. Sorry, I'm trying to move to the next slide. I can't.
Okay.
Oh, there you go.
Try now.
So I don't think I need to introduce QUIC in any detail to this community. So just a very brief thing. It's a security P-based protocol for HTTP3. Protocols are implemented fully in user space, standardized by IETF, and then adopted by many content providers. These are some of the logos I could find for some of the implementations by Meta, Cloudflare, and Microsoft. This implementation flexibility has some upsides, downsides, and really ugly sides. So just as a very brief overview, the good sides is it enables providers to really integrate and customize their implementation with their existing applications. And one publicly available picture of this is what Meta is doing. So Meta has MoveFast, which is integrated with their C++ wrappers and libraries in Folly, as well as their encryption libraries called Fizz. The bad side is, of course, interoperability, which has been studied a lot by this community. And you can see some of the outcomes of this in the QUIC interop runner. This is a sample of the protocol of the implementations out there and their compatibility. In terms of handshakes, this is the H, and then C1 is handshake under corruption. And as you can see, for just handshakes, there's a lot of reds. And then when you introduce corruption in the handshake, there are even more reds. I consider this just bad because you can say, okay, if I'm gonna adapt this, I'm gonna use my own client and my own server. It's bad for interoperability, but it's not the end of the world. The ugly part, at least in my view, is performance, and this is what this talk is about. And what we've found is that there is quite a lot of variability between the performance of these implementations, and it makes it really hard to reason about like which implementation to adapt if you're not building your own from scratch. So before we jump into the results, I just want to put us all on the same page regarding the experimental setup. So we use 2 servers on Cloud Lab. The RTT between them is in the microsecond. The capacity of the NIC is 25 gigabits per second. We measure the throughput of a single QUIC connection, meaning a single connection ID on a single stream. I don't anticipate that using multiple streams will differ here, but this is what we measured. And we implemented what looks like or behaves like IPERF3 for the different implementations of QUIC that we studied. All of them were using AES 128 GCM encryption with OpenSSL. If you use other libraries, you will get very different results. So this is, in order to make apples to apples comparison, all of them are using the same library. So this is the performance of some of the implementations we looked at. On the left-hand side, you see 3 that are performing below 4 gigabits per second for a single connection. Those are the ones we couldn't really see any publicly available blog posts or papers about them trying to optimize their performance for throughput at least. The second 2, Pico Quick, DPDK, and MS Quick, are 2 of the ones that have been optimized for throughput. And then the last one is TCP with TLS, TCP-LS. It's an implementation of TCP plus TLS that provides some of the features you get from Quick. And you see here that there's a big gap between what TCP with TLS can achieve and what Quick can achieve. And the 2 questions that we're trying to answer here is, why is there such variability between the Quick implementations, and can the gap between TCP and Quick be bridged? Like why is it such a large gap? So the first thing that we try to look at is like, how much does customization play a role here? And this is again sample from the implementations we looked at, and it's again, pie charts are not great to walk away with concrete numbers, but what I want you to walk away with here is that the biggest slice in the pie for each implementation is different. For Quickly, it's IO. For Move Fast, it's the actual protocol customization, and then for Pico Quick, it's crypto. When I started my students looking into this, my expectation was that crypto is always going to be the big player, and then everything else is going to be small. But of course, like this is what you get with the current implementation. And our takeaway here is that protocol implementation and IO optimizations play a huge role in defining the bottleneck. Why protocol implementation is not really something that we can do anything about. This is what the operator that implemented this protocol wanted out of the implementation. We can probably play around with IO optimization and crypto. So this is what we move to next. So for IO, what we wanted to understand is whether Linux's UDP IP stack is a problem. So where this is coming from is that TCP on Linux has received many optimizations, and they're used by default. On the other hand, UDP has on Linux received some optimizations, but they're not enabled by default. And the table at the bottom of the slide really highlights this. What you get with UDP with no optimization with iPerf is around 4 gigabits per second. You enable GSO, which is just batching between user space and kernel space. You get close to 15 gigabits per second. You enable the same batching on the receiver side. You get close to 20. You get around 21 gigabits per second, which is very close to what you get with TCP. Note that with TCP you can do actual segmentation uploading where uploading is done, or sorry, with segmentation is done in hardware. But again, this means that a single connection, single UDP or single quick connection should be theoretically able to reach 20 gigabits per second with Linux. To further validate this, we compare 2 stacks, one using Linux with the optimizations and one using kernel bypass. And we're comparing before and after when you move from Linux with optimization to Linux without optimization to Linux with optimization, and Pico Quick without DPDK and then with DPDK. And what you're seeing here is that the performance are comparable with Linux, no optimization, and then when optimized with Linux, and then when optimized with kernel bypass. And our takeaway here is that Linux UDP is not really a problem, and it can reach comparable throughput to Linux TCP as well as kernel bypass UDP. What this leaves in terms of the big chunks in the pie that I showed you earlier is crypto. And to understand the why crypto is so problematic for Quick in particular, we break down its cost into three parts. One is initialization cost, which is the cost of initializing the encryption context per packet. So this is per operation here, meaning per packet. And then function invocation cost, again, this is per packet. And the last part is encryption overhead, which is a function of the data size. So in order to understand the cost of the 2 components, we compare the cost of encrypting 6 MTUs of 1,500 bytes and then 1 jumbo frame of 9,000 bytes. And as you see, the cost of encrypting 1 jumbo frame is roughly half of that of encrypting 6 MTU 1,500 byte packets. So decreasing the unit size increases cost quite substantially. And Quick's unit is MTU. On the other hand, TLS uses much larger records. So there is a fundamental block here between or a fundamental gap between what's achievable with TCP TLS and what's achievable with Quick. In other words, if we want Quick to get to TCP level, we need some fundamental changes. To summarize these measurements, protocol implementation, IO, and crypto are the biggest bottleneck. Protocol implementation choices come at a huge cost. Linux UDP is unlikely to be a problem, but crypto is a fundamental bottleneck. So we started thinking, can we provide some guidance for implementation so they don't compromise on their customization, but can still optimize performance? Because the protocol is standardized, but the implementation landscape is currently the Wild West. And what we're doing here is just a proof of concept. It's not meant to be a standard for everyone. It's just to say, if you standardize something or if you provide some guidance, you can actually achieve quite substantially. And our suggestions are actually quite simple: is pipelining the processing of the UDP of the Quick stack. And what we're suggesting here is symmetric pipelining between the client and the server, because the overheads are symmetric. And you've seen this with GSO and GRO on the Linux UDP stack. Some notes that come with pipelining is that you need lockless lightweight communication between stages for both the data plane and the control plane. And also, what we found is that the pipeline configuration is implementation dependent. In particular, this is the pipeline configuration that we found to perform best for move fast, which is Meta's implementation. And this is the one that we found to be best for Quickly. And if you implement those and compare them to the baseline, so the left-hand side here, you have the throughput of the baseline, and then on the right-hand side, you have the throughput of pipeline. What you see is that pipelining can actually dramatically boost the performance of Quick. But again, what I want you to walk away with here is not that pipelining is great. There's nothing new about that. Is that, but more importantly, is that if we provide some guidance on how to design and accelerate these implementations, we can actually achieve better performance without compromising on the things that people like about Quick implementation. So in summary, diversing Quick implementations makes it hard to pick one that works for you. Crypto is a fundamental speed bump, and pipelining can actually provide some improvements when it comes to throughput. Thank you.
Jana Iyengar, Netflix. Thank you for the presentation, and I haven't read the paper, so I'll admit that I don't know the details here. But I have 2 points. One of them is a question, perhaps, or maybe I'll just make the comments and I'll let you respond. The first one is, I would strongly encourage, if you haven't yet, to reach out to the implementers. Most of these implementers are actually, and you aren't here in person, but they are at the IETF, and this is a wonderful place to actually talk to them. I'm saying that also in part because I'm familiar with some of the measurements that I've seen, and those numbers are different. They are higher than what you're able to see. And it could point to something in the setup that might be simple enough to change to actually get to the real bottlenecks. The second comment I wanted to make is that a lot of these implementations are typically optimized for one side of the connection. So the Quickly and the move fast implementations, I don't want to speak for the move fast one, but certainly is more optimized to be a server-side implementation and not a client one. So if you actually use this client that is provided with the stack, it is likely to be a client that is not going to be very careful about things like hacking and about receiver flow control advertisements and things like that. So you are potentially also measuring something that is not an optimized path overall, and because oftentimes they are tested with only one end, and the other end is actually an optimized client implementation, such as the Google one, for example. So those are just 2 points, and I'll let you respond.
No, thank you. This is actually great because it gives you more time to talk about some of the things we've done. So first of all, we've been in talk with at least Google and Microsoft on this end, but you're right about the numbers. So these are numbers that we got from versions that were released maybe 2 years ago. And we started with this like maybe 4 years ago. And between each release, there's substantial improvements. The So I wouldn't walk away from this talk or from this paper with the raw numbers. They change. Like when we started working with MoveFast, the maximum throughput it could achieve was hundreds of megabits per second. When we, like 2 years later, it was able to achieve 4 gigabits per second. It's still nowhere near TCP. It's much better than it was. So I wouldn't walk away with the raw numbers. Like so that's one side. Then for the other side regarding optimizations, again, you're absolutely right. What we tried to do with our setup was to put them on even ground. So whatever we're doing for the client in one of them, we're doing for all the clients. What we're doing on the server side for one of them, we're doing for the server side. And again, this is what we can tune. We can't do anything about them or the developers optimizing completely a lot of operations in the server and ignoring the client or absolutely ignoring the client. But we try to level the playing field as much as we could. But again, when it comes to complex optimizations, this was just one of the points we're trying to make. It is what you optimize for. But if you again sidestep that, there's a lot of performance improvements to be made without compromising those optimizations, without really asking the developers to change completely the way they're doing things. But thank you. Those are very good points. Thank you.
Okay. Hi, Lukas Hagen, Hasso-Plattner Institute. I was wondering whether you talked a lot about sort of quick throughput. Did you ever measure something like overhead latency, something like download a small file and see whether sort of maybe your pipeline setup, because it takes, I don't know, a short amount of time to set up, actually increases the latency despite making sort of the overall performance better, and maybe to see if there's like a trade-off or if it's just good to add your pipeline.
Great question. So we did a little bit of that, although we don't report on it in the paper because honestly it wasn't that interesting. Our pipelining approach leverages very lightweight schemes, so we add microseconds of overhead. Those microseconds will be overblown in our setup where the RTT in the setup is microsecond scale. But if you're deploying this on the internet, it will have almost no visible impact on the delay that you're observing.
Okay, thank you.
Thank you.
Okay, thank you, Ahmed. So our next speaker is Catherine Elmenhorst. She's a research associate at Osnabrück University. The majority of her work that she'll be presenting is during her time at RWTH Aachen University and Ericsson Research. She's interested in transport protocol analysis and measurement and internet fragmentation and censorship topics. And she'll be talking about cascades of nested acknowledgements in multi-hop mask.
Okay, thanks. Hi and welcome to my talk. I'm Katrin Elmenhorst and this is joint work with Mirja Kühlewind, Eik Kunze, Konstantin Sander and Klaus Werde. We know that privacy on the internet is not a given. Among many other identifiers, the IP addresses can be used to identify services and also track user behavior across sessions. And to combat this, proxying and tunneling tools help hiding end-to-end IP addresses from path observers, for example, VPNs or Tor, and they do so using different custom or general purpose tunneling protocols. Now we have QUIC as an alternative transport protocol, and QUIC actually provides advantages for tunneling due to its built-in encryption, faster connection setup, and it also provides an unreliable yet congestion-controlled transport option. And yeah, seeing these advantages, the mask working group here in the IETF has developed a new mechanism for tunneling UDP through QUIC. And yeah, a bit simplified, the basic mechanism is that we have a mask client, a mask proxy, and an end-to-end target server. And yeah, the tunnel between the client and the proxy is an unreliable QUIC connection, which provides the encapsulation and the encryption. And this unreliability comes from using QUIC datagram frames for encapsulating the end-to-end payload. And these datagram frames are not retransmitted when lost, but they are still congestion controlled. So if a packet contains a datagram frame, then this will elicit an acknowledgement at the receiver. Mask can also be deployed in a multi-hop fashion, and in this case, the client negotiates a chain of proxies and manages multiple nested tunnels. And this has already been deployed as part of Apple's private relay feature, which proxies all Safari traffic through two masked proxies. And since this could potentially have a large impact on overall web traffic, there is some previous work on privacy and performance aspects. But we, in contrast, wanted to investigate multi-hop mask performance more generally, independently from the specific infrastructure, and also using more than two proxies, for example, for a more strict privacy use case. As part of this investigation, we stumbled upon an interesting phenomenon that I will just try to illustrate for you here now. Let's consider a setting with 3 masked proxies, and then the connection is already established, so the server sends a data packet to the client, and it is encapsulated at each proxy with this datagram frame. And as datagram frames are egg eliciting, we get an acknowledgement on every nested quick tunnel. And of course, we also get the end-to-end acknowledgement. That's all. No, actually not. Now let's just look at this end-to-end acknowledgement a little bit more closely. This is, of course, also encapsulated and tunneled all the way. So as we have learned, datagram frames are egg eliciting, so we get some more acknowledgements, and then we can actually play this again, and we get acknowledgements of acknowledgements of acknowledgements due to this one encapsulated end-to-end acknowledgement. Yeah, this is not so good. The main root cause, as I said, is that encapsulation in mask makes acknowledgements egg eliciting themselves, and this escalates when having multiple nested tunnels. We analyzed kind of the scale of this. This is not working anymore. Oh.
It's just slow.
Let's go.
Delayed.
Okay. Let's just stay here. Yeah, we analyzed the scale, and we saw that in the worst case, the number of acknowledgements depends exponentially on the number of proxies, which sounds really bad, but we also analyzed that increasing the acknowledgement delay and therefore aggregating more acknowledgements can really help with this overhead. And any useful quick implementation would always do some kind of acknowledgement aggregation instead of just using a single acknowledgement for a single packet. So yeah, we wanted to measure the impact of our cascades on using practical egg handling. And for that, we used a Docker-based setup with 0 to 4 proxies. We used Linux traffic control to emulate some fixed end-to-end delay and also 2 different bandwidth scenarios. And used for the mask client and proxies 2 different mask-enabled quick stacks, AOQuick written in Python and Chromium in C++. And then just did a download from the server to the client and did 50 repetitions per run. Okay, so now we evaluated this based on the percentage of bytes from all transmitted bytes that are just attributed to acknowledgements on the mask tunnels. And we first focus on a naive case where we configure a small acknowledgement delay of 1 millisecond. And yeah, I mean, the good news is that this trend between the 1 and the 4 proxies does not look so exponential. So our default packetization mechanisms in the quick stacks and also this 1 millisecond acknowledgement delay already helps reducing kind of the worst case impact that we analyzed. However, we still have substantial overhead just caused by these acknowledgements of acknowledgements of acknowledgements we saw before, with up to 13% of acknowledgement overhead just on mask tunnels in the 4 proxy case. So yeah, we thought, how can we mitigate this effect even more? And our first approach is to just increase the aggregation of acknowledgements on the tunnel connections. So we don't make any assumptions about the end-to-end connection by just increasing the acknowledgement delay. And then the other idea was to just eliminate acknowledgements on mask tunnels altogether by making datagram frames non-eliciting. And this then, of course, requires to disable congestion control because congestion control needs acknowledgements. And then one could argue maybe this is not why we would want to use quick in the first place. But we wanted to have this as a lower bound of the acknowledgement overhead in multi-hop mask. This is what this would be look like to not have acknowledgements for datagram frames. And yeah, for these results, we see that the acknowledgement overhead, of course, goes down a lot when not acknowledging datagram frames. This is the brown case, brown bar. And it also, we have a really good impact when we delay acknowledgements by around 1 round trip time, as you can see in the purple bars here. Which essentially, for example, in the worst case that we saw before, which had 13% of acknowledgement overhead, we now only have around 6%. So to wrap up, what are the main takeaways? We saw an effect that encapsulation in mask makes acknowledgements egg-eliciting themselves, which escalates when having multiple tunnels. We also analyzed that this could potentially be exponential, this effect, dependent on the number of proxies, and saw a practical impact of up to 13% of acknowledgement overhead with 4 proxies. Yeah, and then finally, we saw the potential of increasing acknowledgement delay and aggregation on the mask tunnel connections. And this really highlights the need to consciously configure quick tunnel connections when using multi-hop mask. Yeah, finally, some future work would be to evaluate the impact of these acknowledgements on real-world multi-hop mask deployments. We did some experiments using Apple Private Relay, but there's kind of the hindrance that we don't have access to the proxy infrastructure. And yeah, another interesting thing to look at would be to see the potential of traffic analysis attacks, because these encapsulated acknowledgements that we saw before create a really distinct packet size pattern, and that would definitely be interesting to look into further. So yeah, thank you for your attention, and that's it for me.
Jenna Iyengar, Netflix. Thank you for the talk. I have 2 points again. On the first one, in terms of real practical implications of this thing, typically ACK traffic is going on the reverse path, which is not the high bandwidth part. So in terms of byte overhead, it's not very high. And even though there are multiple ACKs that are being generated, they're being processed at different entities. The client is generating multiple, but that's one that goes to relay 1, that one that goes to relay 2. So in terms of total overhead, all of that is not going to one entity. So you might want to think about that when you're thinking about the analysis of overhead. The question I had for you was, have you looked at the, I haven't been able to look at it in the short time, but you might want to look at the quick aware proxying draft in mask and see if this actually applies there. I don't know if it does.
Yeah, we have done this, but the point with the quick aware extension of mask is that you basically don't have tunnels. So the effect that I was describing does not apply there, because you only forward packets and you don't have this encapsulation that then elicits additional acknowledgements. So that's a very good point, and just using this quick aware extension would eliminate the problem. However, it also maybe has some limitations when it comes to your specific privacy use case, that you might not want to use the simple forwarding, but that you might want to add this additional encryption layer. So it's a trade-off, I guess.
Thank you.
Hey, Lucas Pardew, Cloudflare mask enthusiast. Thanks for presenting this work. As you were presenting through, I was reminded of an issue we had on the datagram draft in 2021 that was opened about maybe we should consider an option to not require datagram acknowledgements at all. And there was a lot of discussion, John was in the thread. We wanted to get the work done. There were potential use cases, but there weren't practical ones. I just wonder if maybe now is the time to consider, this is showing, is there value in acknowledging nested things? Maybe not. So I'm just, if there is interest in that, I would love to hear from people. If there's objections to that, I'd love to hear from people. But yeah, thank you.
Lars?
Lars Deckert, Mozilla, thanks for unlocking the queue. Slow. So for no particular reason, I'm wondering how bad the situation is for a one-hop proxy.
Yeah, I mean, that was in the.
I must have missed it. Sorry.
Yeah. Let's see.
You can just tell me if it's.
So this is kind of the case, and we have around 2% of worst case impact with a single proxy. That's not so much because you essentially, if we consider this kind of exponential growth, then of course it's not as much in the one proxy case.
Jana Iyengar again. That's bandwidth overhead or is that packet overhead?
Sorry?
Is that bandwidth overhead or is that packet overhead?
It's byte overhead. So
byte
it's
overhead.
the percentage of bytes, like considering all transmitted bytes that are just attributed to acknowledgements in the mask tunnels. So it doesn't consider end-to-end acknowledgements either.
I wanted to come into the mic to respond to something that Lucas said earlier. I think there's definitely interest in trying to figure out how to treat these differently, datagrams in general. I'll point out that datagrams are still congestion controlled, so there needs to be some sort of feedback mechanism that allows a sender to sort of open up its window and so on, which is why even when you're doing delaying of the acknowledgements further, you have to be mindful of that. You could consider using the ACK coalescing draft, the draft that we have.
ACK frequency draft?
What's that? ACK frequency, thank you. Yes. The ACK frequency draft as a way to also see if that can help with reducing the number of ACKs.
Yeah, I mean, the underlying problem is that the proxies don't see that there's just an acknowledgement inside. So that's why they generate acknowledgements for acknowledgements, which maybe might not what we want.
Okay, thank you.
Thank you.
So our last talk in the transport section is from Lucas. So he's from the Hasso-Plattner Institute, and he's going to talk about reproducibility. So reproducing and solving a fallback issue in TCP prog.
Thank you. Welcome. I'm Lucas. I'm presenting work on TCP prog. So first up, a lot of you may have already heard of TCP prog, but I'll give a quick. Oh, okay, it works. I'll give a quick summary. So TCP prog is the new proposed congestion control for L4S. And L4S, that's slow, or am I pointing the wrong? I'm pointing in the wrong direction. I'm sorry. And L4S is a new internet architecture to provide low latency and low loss at the full data rate on the public internet. So it's meant to avoid those buffer bloat queues that we've had due to classic congestion controls. And the way they want to do this is by using explicit condition notifications. With the idea being that you could already use them, but for prog, we are going to increase the rate of packets marked as congested, but we're going to reduce our response to each individual packet, and that will then, in turn, similar to data center TCP, lead to smaller queues in front of the bottleneck. But there's a problem with just doing that on the public internet, namely that ECN is already standardized. And you may have the scenario that you have a prog source and a classic source running on a classic bottleneck that has not yet heard of prog or L4S at all. And the problem is, if it has not heard of that, it will just treat all packets equally and will start marking prog packets as much as the old packets. But since we already said that prog is going to respond less to each packet and will respond thereby differently, Prague will starve the other flows on a classic AQM. So this is a fairness issue that might arise during the deployment of L4S on the internet. To solve that, or to combat that, Prague has a fallback, and that fallback is built to detect cases of an RFC 3168 compliant bottleneck AQM. Those are the ones that could potentially misclassify Prague's traffic. And it does that using 3 connection metrics: the smoothed RTT of the connection, the windowed minimum RTT, and the mean RTT deviation. It first computes the Q depth as the difference of the smoothed RTT and windowed minimum RTT. So this is just an estimate, but this is what it uses. And it then compares the Q depth and the mean RTT deviation to reference values. So for the Q depth, the reference value is 2 milliseconds, and for the RTT deviation, the reference value is 750 microseconds. And if they exceed that reference, it's going to control a variable called classic ECN, which is then used by Prague to decide whether to behave like L4S or like one of the old classic flows. And sort of, yeah, the idea is that this now then helps Prague not starve other flows. So this has originally been developed and evaluated extensively by its own authors. They evaluation with different link rates, RTTs, traffic scenarios, and generally found that it does not misclassify classic AQMs in their experiments. And it only rarely misclassified the new L4S AQMs as old AQMs. And they said that this only happens at very low link rates or high RTTs. But now there has been some more recent work that is contradicting that quite strongly. So they did another very simple topology with a fixed link rate of 100 megabits a second and an RTT of 10 milliseconds. So a very standard scenario that has not been marked by the original authors with long-running flows, and they show that Prague completely starves itself on the L4S AQM. So they say that, okay, this algorithm is maybe working a little too good. It's actually limiting Prague itself, but they're not explaining why that is the case. And they then also have a follow-up paper where they have the same issue again, but are again unable to explain that. So in this paper, we set out to investigate this stark difference in the literature to find out whether this is actually now working or not. So we reproduce the results in Mininet. We then extend their findings to different link rates and RTTs because that was something that the original authors mentioned. We then do a root cause analysis using eBPF to find a bug in the current fallback implementation. And we then also visualize the sharing rate of Prague with the patch applied to show that it now actually works. And lastly, we publish our experiment code for reproducibility, of course. So for reproducing, we're using a simple dumbbell topology with different link rates and RTTs and an L4S bottleneck. And we measure Prague's throughput competing against a single classic flow as a percentage of the link rate. And I know these are a lot of numbers, but sort of the high-level summary is on the left, you have Prague versus Cubic. On the right, you have Prague versus BBR. You have the x-axis for data rate, and you have the y-axis for RTT. And just in almost all cases, you can see that Prague is able to only acquire 10 to 20% of the data rate. So here we can definitely see that there is something wrong with the current implementation. So next up, we're going to do a root cause analysis to find out what's going wrong. We do a single run of Prague versus Cubic on dual Pi2, the L4S AQM, at the settings that the original authors also used. And we're going to measure the value of classic ECN every time the congestion window was reduced. So this will tell us whether Prague behaves scalable, L4S-like, or classic. And the results of that show that Prague in our setting is in classic mode almost all of the time. So we see that Prague does fall back on an L4S AQM, which is not what it's supposed to do. Next up, we're going to look at the input parameters. So we're going to look at the Q depth that Prague is estimating, and we're going to look at the RTT deviation. every time classic ECN was updated. So we're going to look at the inputs of that fallback algorithm to see if there's maybe something wrong with our current setup. But as we can see that both values almost never exceed their reference value. They were, yeah, only the QDEF was exceeded that, but the mean of these three values is only barely above the 2000 microseconds of reference value. So we conclude that Prague does fall back, but it should not fall back. And there has to be some bug in the implementation that is causing all of this confusion. And we then did a little bit of digging in the code and we found the issue. So what happened was the entire calculation, this comparing reference values and so forth, was implemented in upscaled integers with a scaling factor of 2 to the power of 24. But that scaling factor for the reference values is actually 2 to the power of 20, which is not obvious, as you can see from the source code, because it's not documented anywhere. And so we presume that it was 20 initially and was then changed to 24, but just someone forgot to update these constants, which then sort of snowballed into a lot of confusion about the algorithm. So sort of you can think of these values instead as being upscaled by the right value, but being a different value. And when you then sort of do that calculation, you get to the point that Prague now thinks its reference QDEF is 1.6 microseconds and its reference RTT deviation is 1.5 microseconds. I mean, both of these are really not achievable in any realistic setting at all. So Prague's fallback is always going to activate, and this is sort of should be the explanation as to what's happening here. So we do the same experiment again, just with the patched kernel. And as you can see, it's now working a lot better. We still have quite a bit of variation between 30 and 70%, and we even have some very low shares in the bottom right corners. Those are the maximum BDP scenarios. That may just be of the limitation of using Mininet, and maybe this is not really handled well there anymore. But in general, we can see that this has fixed the issue, and now it's now more in line with what the authors proposed. And we also looked at the classic ECN variable and checked whether Prague actually still falls back. And that sometimes happens in the leftmost column, which coincides with what the original authors said. But in general, we can see that this is not really an issue anymore. So the other interesting thing is CODL, or a classic AQM. So to see whether this fallback now actually still correctly works when you look at a classic AQM. But our results for that also show that the fallback now correctly works, and it's Prague is now sharing the bottleneck fairly on L4S and classic AQMs. So, in conclusion, we have discovered an issue with Prague's fallback implementation. We have, and we used that to explain the discrepancy in the past literature, and we then also compared the sharing rate of Prague with Cubic on and BBR on CODL and DualPy. And with that, I am open to questions. Thank you.
Any questions? Okay, let's thank the speaker again.
Okay, that was the last presentation in the transport session. So we will now move into the poster session. We have 7 posters in total. 6 of them are up on the wall already to the left of you. One of them will be displayed on screen because it's a remote poster. But first we will have a chance for the poster authors to give a 1-minute pitch on what their posters are about, so that you know what to go and have a look at. So yeah, first up is Niklas Brian Anjaf. He's a graduate student at Carnegie Mellon University, Africa. And he should be online, I hope.
Yes, I am online. Can you hear me?
Yes, we hear you. Go ahead.
Thank you for the introduction. I see my video is disabled. Okay, so over the past decade, we've seen rapid digital growth in Africa that is driven by multiple infrastructure deployments. In our research paper, we set out to investigate whether there's measurement going on for this infrastructure to make sure that there are no blind spots and bottlenecks, and to minimize suboptimal routing and other deployment scenarios. So we quantify measurement across three popular tools. We look at CADA, ANT, and we run trace routes from a vantage point running YAP. And the key notable thing is that internet exchange points have a low coverage across all tools. We then proceed to propose a strategy that involves target selection and vantage point location to be able to bridge this gap and have a better coverage of internet exchange points. Please join us in the paper session, in the poster session, to share with you more details and the assessment on other infrastructure. Thank you.
Thank you, Niklas. And we will have Nicholas on the call here up at the shares table if you want to ask questions. So next up is Andrew Losty. Andrew is a PhD candidate at University College London.
Good afternoon. What I'd like to do is introduce you to my poster. This is a summary of the poster, and we're working, it's UCL and from our colleagues in France in ERA. We're looking at IoT devices and security operations in terms of DNS. So the inputs are security behavior and the regulatory framework. So we're trying to assess how the devices work, what the security implications are. We've got a smart home IoT representation of 30 IoT devices, appliances, televisions, cameras, health, and we're running active experiments, so we're modifying the responses, and passive experiments. And what we're finding, or what I'd like to do on the poster, is to summarize the results. And the aim is to develop a best practice RFC, and we're working with our colleagues at Infoblox on that. And so I think that's a summary as to the poster and the work. Thank you.
Thank you, Andrew. Next up is Paul Edward Bertrand von Uitzel from UC Louvain. But I see his co-author is coming to present.
Yeah, so thank you. So the idea is that if we go back in 2001, we saw that IPv6 was finished, and the next step for IPv6 was to do multi-homing, to have enterprise multi-homing. We did not fully succeed. We designed Shim6 and other solutions, but I think it's time to redo this exercise again, because the idea of having one address per provider is a good idea. And what has changed since then is that everybody has an IPv6 router in his pocket, but it's running Android or iOS. So there is a possibility to switch from your DSL link to your cellular link easily. And if you look at transport protocol with quick migration as with multipath TCP, you have a way to switch from one path to another, which becomes seamless and which allows the applications to change from one provider to another. And so we propose to do switch homing, and you can talk to Paul-Henri and Mathieu to have some ideas about the measurements that they have done. And so they will be on this poster next to the slide.
Okay, thank you, Olivier. Next up, we have Tianyan Yu from Tianyan Yu is a PhD student at UCLA. He will also introduce it online, but we also have Liksha here physically by the poster. Tianyan, are you online?
Yeah, I'm here. Should I present online?
Yes, go ahead, please.
Okay. So let me see. Yeah. So we know Blue Sky is a decentralized social applications, and there are 5 basic components of the Blue Sky. You can have a DNS name as your user handle, and you bind it to a so-called decentralized identifier, which is managed by Blue Sky. Then you can have a personal data server to store your data. And on the consumer side, you can have the labeler to subscribe all the content related by the Blue Sky server, and you can create a feed generator to further create custom feeds for the users. But although the 5 components are supposed to be self-hostable, but in reality, we figured out that almost all the DNS names are actually assigned by the Blue Sky, and the relay, there's only one relay server relate all the contents from all the personal data servers to the consumer side. And in the poster we discussed, there's really 2 technical roadblocks. That is, first, there's no application independent namespace for user identity, and we argue DNS should be a solution which should work for that. And also, if we want to remove the relay from the overall system, there's really no way for the consumer side to discover all the contents from all the PI servers and those 2 technical roadblocks are not unique to Blue Sky, but also to all decentralized applications. And we hope to discuss that in the poster sessions.
Okay, thank you. Then next up, we have Riz Maulana. Riz is a PhD candidate at the Eindhoven University of Technology.
Thank you. Okay, so I'm going to talk about our recent work on struggle-aware observability for flow scheduling. So in this work, we argue that some flow schedulers that prioritize some traffic can generate stragglers. In this case, stragglers are packets with unexpectedly higher queuing delay compared to the other packets from the same flow. So in this right figure is the example when you see a lot of packets coming to different queues with different priorities. The packets that ended up in the lower priority queue can have higher queuing delay. So in this case, it might be stragglers. And the solution that we propose is to develop a tool to detect stragglers directly in the data plane. In this case, we implemented the Tofino switch. So instead of identifying the root cause, we try to identify the victims. And you can see there in the result figure, we try to compare the 5-hour schedule and also the past schedule, and you can see the difference. And this information can be helpful for us to debug or diagnose the flow schedulers. Thank you.
Thank you, Riz. Then next up, we have Yuval Shavit. He's a professor at Tel Aviv University and CTO of BG Protect.
Hi, so we have this tool that can do thousands of DNS queries per second. And in this study, we were looking at billions of queries and found some unstandardized TTL results that should be max-int, but you get basically negative results. If you build systems, it can crash because you can get values that are just non-standard. So,
thank you, Yuval.